Right now, you are hurtling through the universe at 390 miles per second. Since you started this video, you have already traveled over 11,000 miles. But here is the terrifying part. We do not know why. Something out there, something we cannot see, is pulling our entire galaxy toward it. And it is not just us. 100,000 galaxies are being dragged to the same mysterious point. If you enjoy this journey, hit like and subscribe. Now, let us find out what is waiting for us. You have never been still, not once in your entire life. This is a confirmed scientific fact. You are rocketing through the cosmos at a speed that would make a fighter jet look like a parked bicycle. 390 miles per second. That is how fast our galaxy is moving through the universe. To put that into perspective, a bullet fired from a rifle travels about half a mile per second. You are moving nearly 800 times faster than that bullet. Every single moment of every single day. In the time it takes you to blink, you travel about 150 miles. By the time you finish listening to this chapter, you will have crossed more than 200,000 miles of space, and you felt nothing. No wind, no turbulence, no sense of motion at all. This discovery came in the 1970s, when astronomers were studying something called the cosmic microwave background. Think of it as the afterglow of creation itself. When the universe was born nearly 14 billion years ago, it released a flash of light. That light has been traveling through space ever since, stretching and cooling as the universe expanded. Today, it fills every corner of existence as a faint microwave glow. Scientists expected this glow to look the same in every direction. After all, the universe should be uniform on large scales. But when they measured it carefully, they found something strange. The light was slightly bluer in one direction and slightly redder in the opposite direction. This is called the Doppler effect. You experience it every time an ambulance passes you on the street. As it approaches, the siren sounds higher. As it moves away, the siren sounds lower. Light works the same way. When you move toward a source of light, it shifts blue. When you move away, it shifts red. The pattern in the cosmic microwave background told scientists something remarkable. Our entire galaxy was moving, fast, and in a very specific direction. At first, this seemed perfectly normal. The universe is expanding, after all. Everything is moving away from everything else. Scientists call this the Hubble flow, named after the astronomer Edwin Hubble who first discovered it. Surely our movement was just part of this cosmic expansion. But when they did the calculations, something did not add up. Yes, the expansion of the universe explained part of our velocity. And yes, the gravitational pull from nearby galaxies like Andromeda explained a little more, but there was still a huge chunk of our speed that could not be accounted for. We were moving too fast, and we were moving in a direction that made no sense. Something else was out there, something we could not see, something massive enough to drag our entire galaxy off course. The scientists checked their numbers again and again. The result was always the same. We were being pulled towards something. But what could possibly be powerful enough to move an entire galaxy? The answer would take decades to uncover. And when it finally came, it raised even more terrifying questions. To understand what scientists found, you first need to understand how they found it. The cosmic microwave background is not just old light, it is the oldest light in existence. The very first photons that were ever able to travel freely through space. Here is what happened. In the first few 100,000 years after the universe was born, everything was chaos. The cosmos was so hot and so dense that light could not travel anywhere. Photons would burst into existence and immediately slam into particles of matter, getting absorbed or scattered before they could move even a short distance. The universe was opaque, like trying to see through thick fog. Then something changed. As the universe expanded, it cooled. Eventually, about 380,000 years after the beginning, the temperature dropped enough for atoms to form. Suddenly, there was space between particles. Suddenly, light could travel. In that moment, the universe became transparent, and the light that was released in that instant has been traveling ever since. For nearly 14 billion years, those ancient photons have been crossing the void, stretching as space itself expanded, cooling from a blinding white glow to an invisible microwave whisper. When scientists first detected this radiation in 1965, it was one of the most important discoveries in the history of astronomy. It confirmed that the universe had a beginning. It proved the Big Bang theory was correct, and it gave us a snapshot of what the cosmos looked like when it was just an infant. But the cosmic microwave background held another secret, one that would not be fully understood for years. When astronomers mapped this ancient light across the entire sky, they expected to find perfect uniformity. The early universe should have been smooth, with the same temperature everywhere. Instead, they found tiny variations. Some patches of the sky were slightly warmer, some were slightly cooler. The differences were incredibly small, just a few millionths of a degree, but they were real. These fluctuations would later prove to be the seeds of everything we see today. The slightly denser regions would eventually collapse under gravity, forming galaxies, stars, and planets. The slightly emptier regions would become the vast voids between cosmic structures. But there was another pattern hidden in the data, a much larger one. When scientists looked at the overall temperature of the cosmic microwave background, they noticed that one half of the sky was consistently warmer than the other half. This was not a random fluctuation. This was evidence of motion. Our galaxy was plowing through this ancient sea of light at tremendous speed, and the direction of that motion pointed toward a specific patch of sky, a region in the constellation Centaurus. Something in that direction was calling to us, something with enough gravitational power to influence the motion of our entire galaxy across hundreds of millions of light years. Scientists had detected a monster. Now they needed to figure out what it was. Let us pause for a moment to truly grasp what this velocity means for you personally. 390 miles per second sounds abstract. It is just a number. Your brain hears it and files it away without really processing the enormity of what it represents. So let me make it concrete. If you have been listening to this video for about 30 seconds, you have already traveled roughly 12,000 miles through space. That is nearly halfway around the Earth. By the time you finish this single chapter, you will have crossed more than 230,000 miles. That is almost the distance from Earth to the Moon. You did not feel any of it. You cannot feel any of it. And that is perhaps the strangest part of all. Think about the last time you were in a car on the highway. At 70 miles per hour, you could feel the vibration of the engine, see the landscape blur past your window, sense the occasional bump in the road. Now imagine going 500 times faster than that. You should be flattened against your seat, your skin peeling back from the G-forces, your bones cracking under the pressure. Instead, you feel nothing. You could be floating in perfectly still water for all your senses tell you. This is because motion is relative. When everything around you is moving at the same speed and in the same direction, there is no way to detect that movement. The air in your room is moving with you. The ground beneath your feet is moving with you. The entire planet, the entire solar system, the entire galaxy is moving with you. From your perspective, you are perfectly still. It is the rest of the universe that is rushing past. But here is where it gets unsettling. We are not just drifting aimlessly through the cosmos. We are being pulled in a specific direction. Something out there has its gravitational hooks in us, and it is reeling us in like a fish on a line. Every second that passes, we get 390 miles closer to whatever that something is. Every minute, 23,000 miles closer. Every hour, over 1.4 million miles closer. By the end of today, you will be more than 33 million miles closer to the mysterious force that is dragging our galaxy through the void. And you will not feel a thing. Scientists confirmed this movement is real. They confirmed the direction is consistent. They confirmed we are accelerating toward a specific point in space. What they could not confirm, at least not at first, was what exactly we were accelerating toward. The numbers suggested something impossibly massive, something with more gravitational pull than anything we had ever observed, something that seemed to break the rules of what should exist in our universe. They called it the Great Attractor, a name that sounds almost playful, almost innocent. But there was nothing playful about what came next. Scientists are comfortable with uncertainty. They expect it. The universe is vast and complex, and there will always be things we do not understand. But there is a difference between not understanding something and having your understanding actively contradicted by the evidence. That is what happened with the Great Attractor. When astronomers first calculated our galaxy's velocity, they assumed it would be easy to explain. The universe is full of gravitational influences. After all, nearby galaxies pull on us. Distant galaxy clusters pull on us. The overall expansion of space affects our motion. Add it all up, and you should get a number that matches what we observe. Except the numbers did not match. Not even close. The Milky Way is part of what astronomers call the local group. This is a collection of about 40 galaxies bound together by gravity, with our galaxy and Andromeda being the two largest members. The local group, in turn, is part of a larger structure called the Virgo cluster, which contains over 1,000 galaxies. Scientists could measure the gravitational pull from all of these objects. They knew how massive they were, how far away they were, and how their gravity should affect our motion. When they ran the calculations, they found that these influences could explain some of our velocity, but not all of it. There was a gap, a big one. We were moving hundreds of miles per second faster than the known gravitational sources could account for. This meant one of two things. Either our understanding of gravity was fundamentally wrong, or there was something out there that we had not detected yet. Something massive. Something hidden. Most scientists were reluctant to throw out gravity. Einstein's theory of general relativity had been tested countless times and passed every single test. It predicted the motion of planets with extraordinary precision. It explained the bending of light around massive objects. It even predicted the existence of black holes decades before we observed them directly. So if gravity was not the problem, then the mass had to be real. There had to be something out there, something in the direction of the constellation Centaurus, that contained enough mass to yank our entire galaxy off its expected course. The estimated mass was staggering. To produce the gravitational effect scientists were observing, this mysterious object would need to contain the equivalent of 10 quadrillion stellar masses. That is a 10 followed by 15 zeros. More mass than thousands of galaxies combined. At the time, nothing in the known universe came close to that scale. The largest black holes contained billions of stellar masses, not quadrillions. The largest galaxy clusters might approach 1,000 trillion stellar masses, but even those fell short. Whatever the Great Attractor was, it was bigger than anything we had ever imagined, and we had no idea what it could be. Here is where the story takes a darker turn. At first, scientists hoped the Great Attractor might be a local phenomenon. Perhaps something in our immediate cosmic neighborhood was affecting just the Milky Way and a few of our closest neighbors. That would still be strange, but it would be manageable. A localized mystery is easier to solve than a universal one. But when astronomers began measuring the velocities of other galaxies in our region of space, they discovered something far more disturbing. It was not just us. Every galaxy they measured, in every direction around the Great Attractor, was moving toward the same point. Not dozens of galaxies, not hundreds, thousands upon thousands of them. The current estimate is that approximately 100,000 galaxies are being pulled toward the Great Attractor. These galaxies span a region of space more than 500 million light-years across. They include spirals, like the Milky Way, giant ellipticals, dwarf galaxies, and everything in between. They have different ages, different compositions, different histories, and yet they are all moving in the same direction, all being dragged toward the same invisible point in space. Try to picture the scale of this for a moment. A single galaxy contains hundreds of billions of stars. Each of those stars may have planets, moons, asteroids, comets, The total amount of matter in a single galaxy is almost beyond comprehension. Now multiply that by 100,000. All of that matter, all of those stars, all of those worlds, being pulled through the void by a single gravitational source. Whatever the great attractor is, it has enough power to influence a significant fraction of the observable universe. This ruled out most of the obvious explanations. A single massive black hole, even the largest one imaginable, could not produce this effect. A rogue dark matter halo would not have enough concentrated mass. A hidden galaxy cluster might come close, but the numbers still did not quite work. Scientists were forced to consider more exotic possibilities. Perhaps the great attractor was not a single object at all. Perhaps it was something more complex, a structure of some kind that spanned hundreds of millions of light years. But there was a problem, a big one. Every time astronomers tried to point their telescopes at the region where the great attractor should be, they hit a wall. Literally, something was blocking their view, preventing them from seeing what lay in that direction. The universe seemed to be hiding its greatest mystery behind a cosmic curtain, and for decades, scientists could not find a way to peek behind it. Before we go any further, we need to talk about gravity, because gravity is the only thing in the universe powerful enough to do what the great attractor is doing. You probably think you understand gravity. It is the force that keeps your feet on the ground, that makes apples fall from trees, that holds the moon in orbit around the Earth. Simple, right? Not exactly. Gravity is one of the most mysterious forces in nature. We can describe what it does with incredible precision, but we still do not fully understand what it is or how it works. Here is what we know for certain. Every object with mass creates gravity. The more mass an object has, the stronger its gravitational pull, and gravity has infinite range. Unlike other forces that fade to nothing over short distances, gravity extends forever. It gets weaker with distance, but it never completely disappears. This means that every object in the universe is gravitationally connected to every other object. Right now, as you listen to this, you are being pulled ever so slightly by the gravity of distant stars, faraway galaxies, and cosmic structures billions of light years away. The pull is unimaginably weak, far too small to measure or feel, but it exists. When we scale up to galaxies, gravity becomes the dominant force shaping the cosmos. Galaxies do not just drift through space randomly, they follow the gravitational contours of the universe, flowing like water down a hillside toward regions of higher mass. Think of space as a vast rubber sheet. Every object with mass creates a dimple in that sheet. Small objects make small dimples. Massive objects make deep craters. Everything on the sheet naturally rolls toward the deepest points, following the curved surface created by mass. The great attractor is the deepest crater in our corner of the universe. A gravitational well so profound that it pulls on everything within hundreds of millions of light years. But here is the terrifying part. Gravity does not just pull, it also tells us something about what is doing the pulling. The strength of a gravitational field is directly proportional to the amount of mass creating it. So, when scientists measured how strongly the great attractor was pulling on surrounding galaxies, they could calculate how much mass it must contain. The answer was 10 quadrillion stellar masses. That is more than 50,000 Milky Way galaxies combined. More mass in one place than scientists thought possible. Something that massive should be easy to see. It should be blazing with the light of trillions of stars. It should dominate the night sky in its direction. And yet, when astronomers looked, they saw nothing. The great attractor was a gravitational giant hiding in plain sight. And the reason for its invisibility was about to make the mystery even stranger. Imagine trying to study a distant mountain range while standing in the middle of a dense fog. You know the mountains are there. You can feel the wind coming off their slopes. But no matter how hard you strain your eyes, you cannot see them through the haze. That is exactly the problem astronomers faced when trying to observe the great attractor. Our galaxy, the Milky Way, is a spiral structure roughly 100,000 light-years across. Most of its 400 billion stars are concentrated along a flat plane, forming the distinctive band of light we see stretching across the night sky. This plane also contains vast clouds of interstellar dust and gas, the raw materials from which new stars are born. This dust is a problem, a big one. When we try to look out into deep space through the plane of our own galaxy, all that dust and gas gets in the way. It absorbs and scatters visible light, making it impossible to see what lies beyond. It is like trying to look through a frosted window. The glass is there, but everything on the other side is just a blur. Astronomers call this obscured region the zone of avoidance. It is a band around the sky roughly 20 degrees wide, where we essentially cannot see anything outside our own galaxy using normal telescopes. And it blocks our view of approximately 10% of the entire universe. Guess where the Great Attractor happens to be located? Right in the middle of the zone of avoidance, almost exactly centered in the one part of the sky we cannot see clearly. At first, this seemed like terrible cosmic luck. Of all the places in the sky the Great Attractor could have been, it ended up in the one spot hidden from our view. Some scientists even wondered if there was a connection. Perhaps the same structures that created the dust in our galaxy were related to whatever was causing the Great Attractor. That turned out to be a coincidence. Our galaxy's orientation in space has nothing to do with the large-scale structures beyond it. We just happen to end up in a position where the most massive thing in our neighborhood is blocked by our own cosmic backyard. For decades, this was an insurmountable obstacle. Astronomers could measure the Great Attractor's gravitational effects with precision. They could pinpoint its general direction. They could calculate its approximate distance and mass, but they could not actually see it. It was like knowing exactly where a hidden treasure was buried, but being unable to dig it up. The Great Attractor remained a gravitational ghost, felt but never seen, until scientists found a way to see through the fog. Let us talk more about what is actually blocking our view, because the details matter. The interstellar medium is not empty space. It is filled with incredibly thin gas and microscopic dust particles spread across the vast distances between stars. In most places, this material is so sparse that it barely matters. A cubic inch of interstellar space might contain only a few atoms, but when you are looking through hundreds of light years of this material, even tiny densities add up. The dust particles are especially problematic. They are typically smaller than a micron, about 100 times thinner than a human hair. Each individual particle is almost nothing, but trillions upon trillions of them, spread across thousands of light years, create an effective barrier to visible light. Think of it like looking through a very light fog. Any single droplet of water is invisible, but enough droplets together, and you cannot see more than a few feet in front of you. The gas in the interstellar medium causes different problems. It absorbs light at specific wavelengths, creating dark lines in the spectra of distant objects. It also scatters blue light more than red light, causing distant objects to appear redder than they actually are. Astronomers call this interstellar reddening, and it can make objects look fainter and more distant than they really are. In the plane of the Milky Way, where most of this material is concentrated, both effects combine to create an almost impenetrable barrier. Stars that should be visible become invisible. Galaxies that should be bright smudges disappear entirely. The universe beyond our galaxy simply fades to black. The zone of avoidance earned its name because early astronomers noticed that galaxies seemed to avoid this region of the sky. There were fewer galaxies visible near the plane of the Milky Way than anywhere else. Of course, the galaxies were not actually avoiding anything. They were just hidden behind the dust. For the Great Attractor, this created a frustrating paradox. We knew something massive was there. We knew it was pulling on us and thousands of other galaxies. We could calculate its properties with reasonable precision, but we could not confirm its existence visually. Some astronomers worried that they might be wrong. Perhaps the Great Attractor was not a real object at all. Perhaps it was an artifact of measurement errors or flawed assumptions. Without direct observation, there was no way to be completely certain. The mystery needed new technology, new ways of seeing, and fortunately, the universe provides more than one kind of light. Visible light is just a tiny slice of the electromagnetic spectrum. Our eyes evolved to see this particular range because it is the type of light that passes most easily through Earth's atmosphere. But the universe is filled with other kinds of radiation that are invisible to us. Radio waves, infrared light, X-rays, gamma rays. Each of these can tell us things about the cosmos that visible light cannot. And here is the crucial point. Some of these wavelengths can pass through the dust and gas that blocks visible light in the zone of avoidance. Radio waves are especially good at this. Their long wavelengths simply glide past the tiny dust particles that scatter visible light. A radio telescope can peer straight through the plane of the Milky Way as if the dust were not even there. Infrared light is also useful, though not quite as effective. Longer infrared wavelengths can penetrate much of the dust, revealing objects that are completely invisible in optical images. The shorter infrared wavelengths still get blocked, but even partial penetration is better than none. Starting in the 1980s, astronomers began systematic surveys of the zone of avoidance using these new technologies. For the first time, they could glimpse what lay beyond our galaxy's dusty veil. The results were extraordinary. Radio surveys revealed thousands of previously unknown galaxies hiding behind the Milky Way. Infrared observations uncovered massive galaxy clusters that had been completely invisible to optical telescopes. The zone of avoidance turned out to be just as crowded with cosmic structures as any other part of the sky, and in the direction of the Great Attractor, astronomers found something remarkable. Not a single massive object, as some had expected. Not a giant black hole or a rogue dwarf galaxy. Instead, they found an entire cosmic neighborhood hidden behind the curtain. Thousands of galaxies, all concentrated in a relatively small region of space, all part of massive structures that we had never seen before. The Great Attractor was not hiding because it was small or dim. It was hiding because it was behind us, obscured by our own galaxy's dust. When the veil was finally lifted, scientists realized they had been thinking about the Great Attractor all wrong. It was not a thing. It was not an object you could point to and say, "There it is." The Great Attractor was something much bigger, much more complicated, and much more important to our understanding of the universe. When astronomers finally pierced the zone of avoidance, they expected answers. What they got instead was a whole new set of questions. The region around the Great Attractor turned out to be crowded with galaxies, not just a few extra ones hidden by the dust, but thousands of them, packed together in dense concentrations that rivaled anything else in the nearby universe. The first major discovery was the Norma cluster. This is a massive galaxy cluster located about 220 million light-years away, almost exactly in the direction where the Great Attractor was calculated to be. The Norma cluster contains hundreds of galaxies, including several giant ellipticals that dwarf the Milky Way. For a brief moment, scientists thought they had found the answer. Perhaps the Norma cluster was the Great Attractor. Perhaps all those galaxies, combined, contained enough mass to explain the mysterious gravitational pull. But the math did not work out. The Norma cluster is massive, certainly. It contains trillions of stellar masses. But that is still nowhere near the 10 quadrillion stellar masses required to explain the Great Attractor's influence. You would need dozens of Norma clusters, all piled on top of each other, to produce that kind of gravitational pull. Further surveys revealed even more structures. The Norma cluster was not alone. It was surrounded by other clusters, other galaxy concentrations, other massive structures, all packed into the same general region of space. Scientists began to suspect that the Great Attractor was not a single object at all. It was not even a single cluster. It was an entire region of space where mass had accumulated over billions of years, creating a gravitational basin that everything else in the neighborhood was flowing toward. This was a fundamentally different way of thinking about cosmic structures, not as isolated objects floating in empty space, but as parts of a vast, interconnected web where gravity slowly pulled matter into ever larger concentrations. The Great Attractor was not a monster lurking in the dark. It was a drain in the cosmic bathtub, a low point in the gravitational landscape where everything naturally flows. But if that was true, then the Great Attractor was just one piece of an even larger puzzle, because drains do not exist in isolation. They are part of a system. What system was the Great Attractor part of? And how deep did the gravitational rabbit hole go? To understand what the Great Attractor really is, we need to zoom out, way out, far enough to see the structure of the universe itself. From Earth, the night sky looks like a random scattering of stars. But that is an illusion created by our limited perspective. When astronomers map the positions of millions of galaxies across billions of light years, a pattern emerges. The universe is not random at all. It has structure. Scientists call it the cosmic web. It is a vast network of filaments, walls, and nodes, with galaxies clustered along the strands and enormous empty voids in between. If you could somehow see the entire observable universe at once, it would look almost biological, like neurons connected by axons, like foam in a bubble bath, like the structure of life itself. This web did not form by accident. It is a direct consequence of the physics that governed the early universe. When the cosmos was young, matter was distributed almost uniformly. Almost, but not quite. There were tiny fluctuations, regions where matter was slightly denser than average, and regions where it was slightly less dense. These fluctuations were quantum in origin, random variations magnified to cosmic scales by the rapid expansion of space. As the universe aged, gravity went to work on these fluctuations. The denser regions had slightly stronger gravitational pull, so they attracted more matter from their surroundings. The slightly emptier regions lost matter to their denser neighbors. Over billions of years, this process amplified the initial variations into the dramatic structures we see today. Dense regions became denser, empty regions became emptier. Matter collected into filaments and walls, while vast bubbles of nearly empty space opened up between them. The galaxies we see today did not just appear randomly, they formed along the filaments of the cosmic web. In the places where matter was concentrated, galaxy clusters formed at the intersections of filaments, where multiple streams of matter came together, and superclusters formed where multiple clusters gathered into even larger associations. The Great Attractor is not separate from this structure. It is part of it, a particularly dense node in the cosmic web, where filaments converge and matter has accumulated over billions of years. Understanding this changes everything about how we think about our place in the universe. We are not just in a galaxy, we are on a strand of the cosmic web, being pulled toward a gravitational basin created by the structure of the universe itself. Let me walk you through the cosmic hierarchy, because it helps explain what the Great Attractor actually is. Start with a single star. Our nearest stellar neighbor, Proxima Centauri, is about 4 light-years away. A single light-year is roughly 6 trillion miles, so even the closest star is unimaginably far by human standards. Now zoom out. Stars are not distributed evenly through space. They clump together into galaxies. The Milky Way contains somewhere around 400 billion stars, all gravitationally bound together into a vast spinning disk, roughly 100,000 light-years across. Galaxies are not distributed evenly either. They clump together into groups and clusters. The Milky Way belongs to a collection called the Local Group, which contains about 40 galaxies, including Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The Local Group spans roughly 10 million light-years. Zoom out further. Galaxy groups and clusters themselves are not evenly distributed. They gather into superclusters, vast associations containing thousands of galaxies spread across hundreds of millions of light-years. For decades, astronomers thought the Milky Way belonged to something called the Virgo supercluster, a structure about 110 million light-years across, containing at least 100 galaxy groups and clusters. But even superclusters are not the end of the hierarchy. In 2014, astronomers announced the discovery of an even larger structure. They called it Laniakea, a Hawaiian word meaning immense heaven, and it redefined our understanding of where we live in the cosmos. Laniakea is not just a supercluster, it is a supercluster of superclusters, a vast basin of gravitational attraction containing over 100,000 galaxies spread across 520 million light-years. The Virgo supercluster, which we once thought was our cosmic home, turned out to be just one branch of this much larger structure. And here is the key point. The center of Laniakea, the gravitational focus point toward which all of its galaxies are flowing, is located in exactly the same place astronomers had identified as the Great Attractor. The Great Attractor was not a mystery object waiting to be discovered. It was the heart of our cosmic home, the center of a structure so vast that we could not even see its full extent until we developed the technology to map the universe in 3 dimensions. The mystery was solved, but the implications were only beginning. Laniakea changed our understanding of where we are in the universe. Before its discovery, astronomers thought of cosmic structures as fairly static. Galaxies belong to groups. Groups belong to clusters. Clusters belong to superclusters. Each level of the hierarchy was defined by gravitational binding objects held together by their mutual attraction. But Laniakea is different. It is not bound together in the traditional sense. The galaxies within it are not orbiting a common center. They are flowing toward a common center. Think of it like a watershed. When rain falls on a mountain range, the water does not stay where it lands. It flows downhill, following the contours of the terrain, eventually collecting in rivers and lakes at the lowest points. Different drops of rain might land miles apart, but if they are on the same side of the mountain, they will end up in the same river system. Laniakea is a cosmic watershed. The galaxies within it are like raindrops, flowing along the gravitational contours of space toward the lowest point in the landscape. That lowest point, that gravitational drain, is what we call the Great Attractor. The boundaries of Laniakea are defined by this flow. Astronomers mapped the velocities of thousands of galaxies and identified where the flows diverged. Galaxies on one side of the boundary flow toward the Great Attractor. Galaxies on the other side flow toward different attractors, different gravitational basins with their own centers. This was a revolutionary way of thinking about cosmic structure. Instead of defining superclusters by what galaxies are bound together, scientists could define them by how galaxies are moving. The cosmic web was not just a static structure, it was a dynamic one, with rivers of galaxies flowing through it like currents in an ocean. Our galaxy, the Milky Way, is part of this flow. We are one of approximately 100,000 galaxies sliding down the gravitational slope toward the center of Laniakea. We have been falling for billions of years, and we will continue falling for billions more. But here is the strange part. Despite all that falling, we will never reach the center. The universe has one more trick up its sleeve, and it changes everything about our ultimate fate. Let me be absolutely clear about what scientists discovered, because it is easy to misunderstand. The Great Attractor is not an object. You cannot point a telescope at it and take a picture of it. It does not have a surface or a boundary or a specific location you could travel to. The Great Attractor is a place, a region of space, a gravitational center of mass for an enormous cosmic structure. Think about the center of mass of the solar system. It is not located at the surface of the star at the center. It is a point in space, inside but not identical to the star itself. Everything in the solar system orbits around this point, pulled by the combined gravity of all the mass in the system. The Great Attractor works the same way, just on a much larger scale. It is the center of mass of the Laniakea supercluster, the combined gravitational pull of 100,000 galaxies, all pointing toward a single region of space. There is no giant black hole there, consuming everything that approaches. There is no alien megastructure warping spacetime. There is just a concentration of galaxies, clusters, and dark matter, all pulling on the surrounding universe with their combined gravity. The Norma cluster sits near this gravitational center. So do several other massive galaxy clusters. Together, they create the gravitational well that we have been calling the Great Attractor. This might sound like an anticlimax after all the build-up, We spent decades searching for a mysterious cosmic monster, and it turned out to be just more galaxies. But that misses the point. The real discovery was not what the Great Attractor is. The real discovery was what the Great Attractor taught us about the universe, about how matter is distributed on the largest scales, about how gravity shapes the evolution of cosmic structures, about our place in the hierarchy of existence. We are not floating randomly through space. We are part of an enormous system, a vast supercluster with a defined center and defined boundaries. We are flowing toward that center along with 100,000 other galaxies. The Great Attractor was never a monster waiting to devour us. It was a signpost pointing toward our cosmic home, and yet there is one final twist to this story. One last mystery that makes everything more complicated. 10 quadrillion stellar masses. That is the estimated mass of the Great Attractor, the combined gravitational influence pulling 100,000 galaxies toward the center of Laniakea. Let me put that number in perspective. The Milky Way contains roughly 400 billion stars. Many of those stars are smaller than the one at the center of our solar system, and some are larger, but on average, the total mass of our galaxy is roughly 1 to 2 trillion stellar masses when you include dark matter. 10 quadrillion is 10,000 trillion. That means the Great Attractor contains the equivalent of 5,000 to 10,000 Milky Way galaxies. Now, there are about 100,000 galaxies in the Laniakea supercluster. If you add up all their visible mass, you get maybe 500 trillion stellar masses. Impressive, but still far short of 10 quadrillion. Where does the extra mass come from? The answer is dark matter, that mysterious substance that does not emit, absorb, or reflect light, but still exerts gravitational influence on everything around it. Scientists estimate that dark matter makes up about 85% of all mass in the universe. For every pound of normal matter, atoms and molecules and everything we can see and touch, there are roughly 5 pounds of dark matter that remain invisible to all our instruments. The Laniakea supercluster is swimming in dark matter. It fills the spaces between galaxies, surrounds galaxy clusters in enormous halos, and contributes the bulk of the gravitational pull that defines the Great Attractor. This is confirmed science, not speculation. We can see the effects of dark matter in the rotation curves of galaxies, in the bending of light around massive clusters, in the structure of the cosmic microwave background itself. Dark matter is real, even if we do not yet know what it is made of. So the Great Attractor's enormous mass is not unexplained. It comes from the combination of visible galaxies and the dark matter that pervades the supercluster. But understanding where the mass comes from does not make the Great Attractor any less impressive. A gravitational well containing 10 quadrillion stellar masses, pulling on everything within 500 million light-years. Even with all our explanations, the scale remains almost impossible to comprehend, and we are falling into it. Let us talk about distance, because it matters for what comes next. The center of the Great Attractor is located approximately 200 million light-years from Earth. That sounds like an unimaginably large number, and in human terms, it is. Light traveling at 186,000 miles per second would need 200 million years to make the journey. But, in cosmic terms, 200 million light-years is not actually that far. The observable universe is 93 billion light-years across. The Great Attractor is roughly in our cosmic backyard, a nearby structure in the grand scheme of things. This relative closeness is actually important. If the Great Attractor were billions of light-years away, its gravitational influence on us would be negligible. Gravity weakens with distance. Following an inverse square law, double the distance, and the gravitational pull drops to 1/4. Triple the distance, and it drops to 1/9. At 200 million light-years, the Great Attractor is close enough to have a significant gravitational effect on our motion. Not an overwhelming effect, but a measurable one. That is why we are moving toward it at 390 miles per second instead of some much smaller velocity. The travel time at our current speed is approximately 95 billion years. If nothing changed, if we just kept falling toward the Great Attractor at our current velocity, Our distant descendants might eventually reach the center of Laniakea, but something will change. Something is already changing. The universe is not static, it is expanding, and the rate of that expansion is accelerating. Every year, the space between distant objects grows larger. Objects that are far apart today will be farther apart tomorrow. For nearby objects, this expansion is negligible. The Milky Way and Andromeda are close enough that gravity overwhelms the expansion of space, and we are actually moving toward each other. But for objects hundreds of millions of light years away, the expansion starts to matter. The Great Attractor is pulling us toward it, but the expansion of the universe is pushing us away. Right now, the pull is stronger than the push. We are getting closer, but that will not always be true. And when the balance shifts, everything changes. Here is something that would have seemed impossible just a century ago. The universe is expanding, not into something, but everywhere at once. Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. Edwin Hubble discovered this in 1929, when he noticed that distant galaxies were all moving away from us. The farther away a galaxy was, the faster it appeared to be receding. This was not because we were at the center of some cosmic explosion. It was because space itself was growing. Imagine drawing dots on a balloon and then inflating it. Every dot moves away from every other dot, not because the dots are traveling through the balloon's surface, but because the surface itself is expanding. That is what is happening to our universe on the grandest scales. For most of the 20th century, scientists assumed this expansion was slowing down. After all, gravity pulls everything together. The mutual attraction of all the matter in the universe should be acting like a brake, gradually reducing the expansion rate over time. Eventually, they thought, the expansion might even stop or reverse. In 1998, two independent teams of astronomers set out to measure exactly how much the expansion was slowing. They studied a particular type of exploding star called a Type 1a supernova, which always produces roughly the same amount of light. By measuring how bright these explosions appeared from Earth, they could calculate how far away they were, and by measuring how much their light was redshifted, they could determine how fast they were receding. What they found shocked the scientific world. The expansion was not slowing down, it was speeding up. The universe was accelerating. Something was pushing it apart, overcoming the attractive force of gravity, and causing space to expand faster and faster over time. Scientists named this mysterious force dark energy. They have no idea what it is. It does not fit into any existing theory of physics. It makes up roughly 68% of everything in the universe, and yet we cannot detect it directly, cannot explain where it comes from, and cannot predict what it will do in the future. All we know is that it exists, and that it is winning the battle against gravity. This discovery earned the leaders of those two research teams the Nobel Prize in Physics. It also fundamentally changed our understanding of the fate of the universe, and it has direct implications for our journey toward the Great Attractor. Because if the expansion of space is accelerating, then eventually that expansion will overpower the gravitational pull that is currently dragging us toward the center of Laniakea. The race between gravity and dark energy is on, and dark energy is going to win. Let me explain exactly what is happening, because the physics here is strange. Right now, we are moving toward the Great Attractor at 390 miles per second. That velocity is real. It is caused by the gravitational attraction of the mass concentrated at the center of the Laniakea supercluster. If nothing else were happening, we would continue falling toward that center forever, eventually reaching it in about 95 billion years. But something else is happening. The space between us and the Great Attractor is expanding. This expansion is subtle at short distances. Between Earth and the nearest stars, space expands by only a few inches per year. That is far too small to notice or measure. But over larger distances, the effect accumulates. Between us and the Great Attractor, space is expanding by millions of miles every year. Currently, Our velocity toward the great attractor is greater than the expansion rate of the space between us. We are gaining ground. Every year, we are a little bit closer to the center of Laniakea than we were the year before, but the expansion is accelerating. Every year, space grows a little bit faster than it did the previous year, and at some point in the distant future, the expansion rate will exceed our velocity. The space between us and the great attractor will start growing faster than we can cross it. When that happens, we will start moving backward, not in any physical sense. We will still be traveling toward the great attractor at tremendous speed, but the space we are traveling through will be stretching faster than we can traverse it. It will be like running on a treadmill that keeps speeding up. No matter how fast you run, you fall further and further behind. This is not science fiction. This is confirmed cosmology, supported by decades of observations and theoretical work. The accelerating expansion of the universe will eventually overcome the gravitational pull of even the largest structures. The great attractor will slip away from us. The center of our supercluster, the place we have been falling toward for billions of years, will recede into the distance, and there is nothing we can do about it. Gravity gave us a destination. Dark energy is taking it away. But the consequences go far beyond missing our appointment with the great attractor, because the accelerating expansion will not just affect our journey to Laniakea. It will affect everything. There is a boundary in the universe that most people have never heard of. Scientists call it the cosmic event horizon, and it represents the ultimate limit of what we can ever observe or reach. The concept is similar to the event horizon of a black hole. Once something crosses a black hole's event horizon, it can never escape. The gravity is too strong, the escape velocity too high. Even light, traveling at the fastest possible speed, cannot outrun the pull. The cosmic event horizon works differently, but the result is the same. It is the distance at which the expansion of space equals the speed of light. Beyond this boundary, objects are receding from us so fast that their light will never reach us. They are not traveling faster than light through space. Space itself is carrying them away at an effective speed greater than light can overcome. Today, the cosmic event horizon is roughly 16 billion light-years away. Objects beyond that distance are effectively cut off from us forever. We will never see them, never visit them, never receive any signal from them. They exist, but they are permanently beyond our reach. And here is the terrifying part. The cosmic event horizon is shrinking. As the expansion of the universe accelerates, more and more objects are crossing beyond the horizon. Galaxies that were once within our observable universe are being swept away, their light stretched to invisibility, their existence erased from our sky. This process is slow. On human timescales, it is imperceptible. But over billions of years, it will transform the universe we see. The Virgo cluster, a nearby concentration of galaxies just 50 million light-years away, will eventually cross the horizon and disappear. So will the great galaxy clusters and superclusters that dot our cosmic neighborhood. One by one, they will slip beyond the boundary and vanish from view. Even the great attractor, the gravitational center we have been discussing throughout this video, will eventually be lost. The expansion of space will carry it beyond our cosmic event horizon, and it will cease to exist as far as we are concerned. The universe will become smaller, not physically smaller, but observationally smaller. The bubble of reality we can access will shrink until only our immediate neighborhood remains. And eventually, even that will not be enough. Not everything will be swept away by the expanding universe. Some things are close enough and gravitationally bound tightly enough to resist the cosmic tide. The Milky Way and Andromeda are moving toward each other at about 70 miles per second. In roughly 4 billion years, the two galaxies will collide and merge, forming a single enormous elliptical galaxy that some astronomers have nicknamed Milkomeda. This collision will happen regardless of the expansion of the universe. The gravitational attraction between the Milky Way and Andromeda is strong enough to overcome the expansion of the relatively small amount of space between them. They are bound together locked in a gravitational embrace that will eventually pull them into one. The same is true for the other galaxies in the local group. About 40 galaxies, including several dozen dwarf galaxies orbiting the Milky Way and Andromeda, are all gravitationally bound to each other. They form a stable system that will persist even as the rest of the universe recedes. This is good news, in a sense. Our descendants, whether human or whatever species might follow us, will have company. They will not be alone in a single isolated galaxy. They will have access to the merged remnants of the entire local group, a collection of hundreds of billions of stars. But that is it. That is all they will have. The Virgo cluster, with its thousands of galaxies, will drift away beyond the cosmic horizon. The Laniakea supercluster, with its 100,000 galaxies, will vanish into the expanding void. The cosmic web, that vast interconnected structure spanning billions of light years, will fade from view entirely. Future astronomers, billions of years from now, will look up at the night sky and see nothing but the stars of their own local merged galaxy. They will have no evidence that the universe contains anything else. No other galaxies visible, no cosmic structures to map, no hint of the vast web of matter that once filled the observable universe. They might conclude that their galaxy is the entire universe, that nothing exists beyond the stars they can see. And, in a practical sense, they would be right, because everything else will be forever beyond their reach. Picture the night sky as it might appear 100 billion years from now. The familiar constellations are long gone. The individual stars that make up Orion and the Big Dipper exhausted their fuel billions of years ago. In their place is a smooth glow, the combined light of hundreds of billions of stars in the merged Milky galaxy. But beyond that glow, there is nothing, absolute darkness. No distant smudges of light that might be other galaxies. No cosmic microwave background radiation providing a faint warmth to the void. Just endless, empty blackness stretching in every direction. This is not a temporary condition. It is permanent. No matter how long future observers wait, no new light will arrive from beyond the cosmic horizon. The information is gone. The photons that might have told them about other galaxies are stretched to infinite wavelengths, redshifted out of existence by the relentless expansion of space. Future scientists might discover the expansion of the universe through other means. They might notice that the stars in their galaxy are gradually moving apart. They might detect subtle variations in the structure of space-time, but they will have no way to know what the universe once looked like. No way to know that billions of other galaxies once filled the sky. The cosmic web that we can see today, the vast structures that contain the Great Attractor and the Laniakea supercluster, and countless other wonders, will be completely erased from the observable universe. It will be as though they never existed. This is one of the most unsettling implications of modern cosmology. We happen to live at a special time in the history of the universe, a time when we can still see the large-scale structure of reality, a time when the evidence for the Big Bang is still visible in the cosmic microwave background, a time when other galaxies are still close enough to study. Future civilizations will not have these advantages. They will be cosmologically blind, unable to reconstruct the history or structure of the universe beyond their own isolated island of stars. We are lucky. We are living in the age of discovery, when the universe still reveals its secrets to those who look. But that age will end. Let me bring this back to where we started. You, sitting wherever you are, hurtling through space at 390 miles per second toward a gravitational center you will never reach. The Great Attractor is not going to swallow us. It is not a threat. It is not going to destroy the Earth or disrupt the solar system or cause any problems for human civilization. The timescales involved are so vast that our species will likely be long gone before any of these cosmic dynamics significantly affect our corner of the universe. But that does not mean the Great Attractor is irrelevant. Understanding it teaches us something profound about the nature of existence. We are not floating randomly through an empty void. We are embedded in a structure. We are part of a cosmic flow, a river of galaxies all moving together toward a common destination. Our motion through space is not arbitrary. It has a direction, a purpose, a gravitational logic. The Laniakea supercluster is our home in a way that goes beyond simple location. It defines the gravitational environment we exist in. It shapes the motion of our galaxy. It connects us to 100,000 other galaxies in a vast cosmic family. When ancient humans looked up at the night sky, they saw patterns and invented stories to explain them. They imagined gods and monsters and heroes among the stars. They tried to find meaning in the seemingly random scattering of lights above their heads. Modern astronomy has revealed something even more remarkable than those ancient myths. The universe has real structure, real connections, real flows of matter and energy that span hundreds of millions of light years. We are not observers standing outside this structure. We are participants in it, carried along by forces that were set in motion billions of years before our planet even formed. The Great Attractor is a reminder that we are small, cosmically insignificant, a tiny speck of matter on a tiny planet orbiting a typical star in an ordinary galaxy in one branch of a vast supercluster. But it is also a reminder that we are part of something much larger than ourselves, connected to the universe in ways we are only beginning to understand. The story does not end with the Great Attractor. It does not even end with the Laniakea supercluster. When astronomers mapped the flows of galaxies in our region of space, they discovered that Laniakea itself is moving. The entire supercluster, all 100,000 galaxies, is being pulled towards something even larger. That something is called the Shapley supercluster, located about 650 million light-years away. It is one of the most massive concentrations of matter in the nearby universe, containing at least 40 galaxy clusters and thousands of individual galaxies. Its gravitational pull extends across hundreds of millions of light-years, influencing the motion of everything in its vicinity, including us. The Great Attractor pulls us toward the center of Laniakea, but the Shapley supercluster pulls Laniakea itself in a specific direction. We are caught in a hierarchy of gravitational influences, like a leaf floating in a stream that is itself flowing into a larger river. And even the Shapley supercluster is not the end. Recent observations suggest that there may be even larger structures beyond it, concentrations of mass so vast that they affect the motion of multiple superclusters simultaneously. The universe is fractal in its complexity. Every time we zoom out, we find larger structures containing the smaller ones we already knew about. Stars form galaxies, galaxies form clusters, clusters form superclusters, and superclusters may form even larger associations that we are only beginning to detect. Where does it end? We do not know. The observable universe has limits, and beyond those limits we cannot see. There may be structures larger than anything we have discovered, gravitational influences extending across billions of light-years that we have no way to measure. The Great Attractor taught us that we are part of a cosmic flow. But it also taught us that there are always larger flows, bigger structures, deeper mysteries waiting to be discovered. The universe is not just big, it is nested, layer upon layer of structure, each one containing and being contained by others. And somewhere in all of that, on a small planet orbiting an ordinary star, you are listening to these words. We have solved the mystery of the Great Attractor. We know it is the gravitational center of the Laniakea supercluster, a concentration of mass created by the combined pull of 100,000 galaxies and the dark matter that surrounds them. But solving one mystery has only opened the door to others. Dark matter remains one of the greatest unsolved problems in physics. We know it exists. We can measure its gravitational effects. We can map its distribution across the universe. But we have no idea what it is made of. Every experiment designed to detect dark matter particles directly has come up empty. Whatever dark matter is, it does not interact with normal matter in any way we can detect except through gravity. Dark energy is even more mysterious. It makes up 68% of the total energy content of the universe, yet we know almost nothing about it. We do not know why it exists. what causes it, or whether it will continue to behave the same way in the future. Some theories suggest dark energy might change over time, potentially leading to scenarios where the universe tears itself apart at the smallest scales. The accelerating expansion of the universe is confirmed by multiple independent lines of evidence, but the underlying cause remains completely unknown. We have given it a name, dark energy, but that name is really just a label for our ignorance. And then there are the structures themselves. We can map the cosmic web, trace the flows of galaxies, identify superclusters and voids, but we still do not fully understand why the structures have the specific properties they do. Why are galaxy clusters the size they are? Why do voids grow to certain dimensions and then stop? What determined the particular pattern of the cosmic web? The Great Attractor answered one question and raised a dozen more. That is how science works. Every discovery reveals new mysteries, new frontiers of ignorance to explore. We know more about the universe than any previous generation of humans. And yet the more we learn, the more we realize how much we still do not know. Let us return one final time to where this journey began. You, moving through space at 390 miles per second, traveling toward a destination you will never reach. By now, you have traveled further than you might imagine. If you started this video 30 minutes ago, you have crossed more than 700,000 miles. That is roughly 3 times the distance from Earth to the Moon, all without moving a muscle, without feeling a thing. Tomorrow, you will have traveled another 33 million miles. Next year, more than 12 billion miles. In your lifetime, assuming you live another 50 years, you will travel over 600 trillion miles through the cosmos, and you will still be nowhere close to the Great Attractor. The distances involved are so vast that human lifetimes become meaningless. The timescales are so long that entire civilizations rise and fall in the blink of a cosmic eye. The forces shaping our motion through space have been operating for billions of years and will continue for billions more. But here is what makes it meaningful. You are aware of it. You are one of the only arrangements of matter in the known universe capable of understanding these facts. The galaxies do not know they are being pulled toward the Great Attractor. The stars do not know they are part of a cosmic flow. Only conscious beings like you can comprehend the structure of the universe and their place within it. That makes you special. Not because you are at the center of things. You are not. Not because you are particularly large or powerful or important. You are not. But because you can look up at the night sky and ask why. Why are we moving? What is pulling us? Where are we going? What does it all mean? Those questions matter. The universe created beings capable of wondering about the universe. And every answer we find reveals new questions worth asking. We have reached the end of this exploration, but the journey never really ends. The Great Attractor will continue pulling us toward the center of Laniakea for billions of years to come. The expansion of the universe will eventually overcome that pull, carrying the Great Attractor beyond our cosmic horizon. The galaxies of the local group will merge into a single island of stars, alone in an infinite void. These are the facts as we understand them today, confirmed by decades of observations, supported by our best theories of physics and cosmology. But science is never finished. New discoveries might change our understanding. New observations might reveal structures and forces we never imagined. A century ago, we did not know other galaxies existed. 50 years ago, we did not know the universe was accelerating. 20 years ago, we did not know about the Laniakea supercluster. What will we discover in the next 20 years? The next 50? The next century? The Great Attractor was once a complete mystery, a gravitational ghost pulling our galaxy in a direction we could not explain. Now we understand what it is, where it is, and why it affects us. But that understanding only came because generations of scientists kept asking questions, kept building better instruments, kept pushing the boundaries of human knowledge. You are part of that tradition now. By listening to this video, by thinking about these ideas, you have joined the long human project of trying to understand the cosmos. You have wondered about the same questions that have driven astronomers for centuries. Where are we? How did we get here? Where are we going? The answers are strange and beautiful and terrifying. The universe is vast beyond comprehension, structured in ways we are only beginning to map. We are small, temporary, insignificant by any cosmic measure, and yet we are here. We are aware. We are asking questions. That has to count for something. Thank you for watching. If you enjoyed this journey through the cosmos, please like and subscribe for more explorations of the strange and wonderful universe we call home. We have spent this entire journey talking about what is pulling us. But here is something most people never hear about. Something is also pushing us. In 2017, astronomers announced a remarkable discovery. They had been mapping the motion of galaxies in our region of space with unprecedented precision, trying to understand all the forces affecting our velocity. And they found something unexpected. Behind us, in the opposite direction from the Great Attractor, lies a vast region of emptiness. Not just ordinary emptiness. A void so profound, so devoid of matter, that it creates a kind of negative gravitational effect. Scientists named it the dipole repeller. Think about how gravity works. Mass attracts mass. The more matter concentrated in one place, the stronger the pull toward that place. But the reverse is also true. Regions with less matter than average create a relative push away from themselves. Imagine standing on a hillside. Gravity pulls you downward toward the valley, but you could also describe your motion as being pushed away from the hilltop. Both descriptions are mathematically equivalent. The Great Attractor is the valley we are falling into. The dipole repeller is the hilltop we are falling away from. The dipole repeller is located roughly 750 million light-years away in the direction of the constellation Pisces. It is not a physical object pushing against us. It is an absence. A region where galaxies failed to form, where matter is scarce, where the cosmic web has a hole. Before this discovery, astronomers could only explain about half of our galaxy's peculiar velocity using known mass concentrations like the Great Attractor and the Shapley supercluster. The other half remained mysterious. Adding the dipole repeller to the calculations finally made the numbers work. We are caught between two cosmic forces. Ahead of us, the concentrated mass of the Laniakea supercluster pulls us forward. Behind us, the emptiness of the dipole repeller lets us fall away. Together, these two effects combine to produce our total velocity of 390 miles per second. This changes how we think about cosmic motion. It is not just about attraction. It is about the full landscape of mass and emptiness, hills and valleys, distributed across hundreds of millions of light-years. Our motion is determined by everything around us, not just the things that pull. The universe is even more structured than we thought. Not just concentrations of matter, but carefully arranged voids pushing galaxies in specific directions. And the dipole repeller is not alone. There may be other great voids out there, other regions of emptiness influencing the motion of galaxies in ways we have not yet detected. The cosmic web is not just made of threads. It is also made of the spaces between them. 4 billion years from now, the night sky will look very different. A massive spiral galaxy will dominate the heavens, stretching from horizon to horizon. It will be Andromeda, and it will be heading straight for us. The Milky Way and Andromeda are on a collision course. This is confirmed science, measured through precise observations of Andromeda's motion toward us. The two galaxies are approaching each other at roughly 70 miles per second. In cosmic terms, that is a gentle drift. But given enough time, even gentle drifts lead to dramatic outcomes. When the galaxies finally meet, the collision will unfold over hundreds of millions of years. Stars will not actually crash into each other. The distances between individual stars are too vast for that. If you shrunk our stellar neighbor down to the size of a grain of sand, the nearest other grain would be about 4 miles away. Even when two galaxies merge, the grains almost never touch, but the gravitational chaos will be extraordinary. Stars will be flung out of their orbits, sent spinning into intergalactic space. Gas clouds will collide and compress, triggering massive bursts of star formation. The familiar spiral shapes of both galaxies will be torn apart and eventually settle into a single bloated elliptical structure. Astronomers have run detailed simulations of this merger. They show our solar system being thrown into wild new orbits, possibly flung far from the galactic center, possibly dragged closer to the dense core. The good news is that Earth will probably survive the gravitational disruption. The bad news is that by then, our planet will already be uninhabitable for other reasons. This collision will happen regardless of the great attractor, regardless of the expansion of the universe. The Milky Way and Andromeda are gravitationally bound to each other, locked together by their mutual attraction. No force in the cosmos can prevent their eventual merger. The resulting galaxy has already been given a name, Milkomeda. Some astronomers prefer Milkdromeda. Either way, it will be the final home of whatever remains of our stellar neighborhood. After the merger completes, roughly 6 billion years from now, Milkomeda will begin its long isolation. The expansion of the universe will carry everything else away, and our descendants, if any exist, will live in a galaxy that is truly alone. But before that loneliness arrives, there will be fireworks. Stars are born, burn through their fuel, and die. This is basic astronomy, taught in every introductory course. But galaxies also have lifespans, and their deaths are far stranger than any individual star. A galaxy does not die all at once. It fades, slowly, over timescales that make human history look like a single heartbeat. The Milky Way is currently forming new stars at a rate of about 1 to 2 per year. That sounds slow, but over billions of years, it adds up. These new stars replace the ones that die, keeping the galaxy vibrant and luminous. But star formation requires raw material, gas and dust, the ingredients from which stars are made, and that supply is finite. Every time a new star forms, it consumes some of the available gas. Some of that gas is returned when the star dies, expelled in stellar winds or supernova explosions, but not all of it. Each generation of stars locks away a little more matter in stellar remnants. White dwarfs, neutron stars, black holes. These objects do not give back what they took. Over billions of years, the supply of star-forming gas dwindles. New stars become rarer and rarer. The galaxy grows dimmer as its oldest stars burn out and fewer replacements are born. Eventually, star formation stops entirely. The last generation of stars lives out its lifespan, and then silence. No new lights appear in the darkness. The galaxy becomes a graveyard of cooling stellar corpses, slowly fading toward absolute black. This process takes trillions of years, far longer than the current age of the universe. But it is inevitable. Every galaxy faces this fate, including the merged Milkomeda that will one day be our home. The great attractor cannot save us from this. Falling toward the center of Laniakea does not provide new fuel for star formation. The cosmic flow continues, but it leads nowhere that can prevent the eventual dimming of all lights. Galaxies are not eternal. They are just very, very long-lived. And in the grand scheme of cosmic time, even that is temporary. When a star dies, it does not simply vanish. It leaves behind a corpse. And those corpses accumulate over billions of years, filling the galaxy with the remnants of ancient fires. Small stars, like red dwarfs, burn so slowly that none have ever died since the universe began. They will continue shining for trillions of years, the last lights in a darkening cosmos. But they are dim, barely visible, even from nearby. Medium-sized stars like the one at the center of our solar system end their lives more dramatically. They swell into red giants, shed their outer layers into beautiful planetary nebulae, and collapse into white dwarfs. These dense stellar remnants are about the size of Earth but contain the mass of an entire star. They glow with residual heat, slowly cooling over billions of years. Massive stars die in explosions, supernovae that outshine entire galaxies for brief moments. What remains depends on the original star's mass. Some leave behind neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons. Others collapse completely into black holes, regions of space-time so warped that nothing can escape. As the universe ages, these remnants accumulate. White dwarfs cool into black dwarfs, invisible spheres of crystallized carbon floating through the void. Neutron stars spin down and go silent. Black holes slowly evaporate through a process called Hawking radiation, though this takes unimaginably long times. The future universe will be filled with these corpses, trillions upon trillions of dead stars, drifting through galaxies that no longer produce light. The cosmic flow toward the great attractor will continue, but it will be a flow of darkness, of cold matter, of remnants. This is not science fiction. This is the confirmed trajectory of stellar evolution, extrapolated across cosmic time. The universe had a bright beginning, and it will have a dark ending. The great attractor exists in a universe that is still young, still vibrant, still producing new stars. But that vibrancy is temporary. The lights are going out, slowly, one by one, across billions of years, and nothing can stop it. 390 miles per second sounds fast, and it is, by human standards. But in the cosmic speed rankings, our galaxy is actually quite ordinary. Let us put our velocity in context. The International Space Station orbits Earth at about 5 miles per second, fast enough to circle the planet every 90 minutes. The space station is one of the fastest human-made objects in regular operation. Earth orbits its star at roughly 18 miles per second. That is why we experience seasons, why the constellations shift throughout the year, why the night sky looks different in summer than in winter. Our entire solar system orbits the center of the Milky Way at about 130 miles per second. At that speed, it still takes roughly 230 million years to complete a single orbit. The last time we were at this point in our galactic journey, dinosaurs had not yet evolved. And then there is our motion toward the great attractor, 390 miles per second, carrying us through intergalactic space toward the center of Laniakea. But even that is not the fastest thing in the cosmos. Some galaxies in distant clusters are moving at over 1,000 miles per second relative to their neighbors. Quasars, powered by supermassive black holes, consuming matter at tremendous rates, shoot jets of material at nearly the speed of light, and photons themselves travel at 186,000 miles per second, the universal speed limit that nothing with mass can ever reach. Our 390 miles per second is impressive, but it is a gentle stroll compared to the extremes the universe can produce. What makes our velocity special is not its magnitude, it is what it tells us. Our speed and direction reveal the gravitational landscape around us. They expose the hidden structures pulling on our galaxy. They connect us to a cosmic web that spans hundreds of millions of light years. Speed is information, and our speed is telling us a story about where we are and where we belong. There is another way to detect massive objects in the universe, and it does not require seeing them at all. In 1915, Albert Einstein predicted that massive objects moving through space would create ripples in the fabric of space-time itself. He called them gravitational waves. Like ripples spreading across a pond when you throw in a stone, these waves would propagate outward at the speed of light, carrying information about the events that created them. For a century, gravitational waves remained purely theoretical. They were too weak to detect with any technology we possessed. Einstein himself doubted we would ever observe them directly. Then, in 2015, everything changed. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. They came from two black holes spiraling into each other over 1 billion light-years away. The collision released more energy than all the stars in the observable universe combined, and some of that energy reached Earth as a tiny ripple in space-time. How tiny? The gravitational waves stretched and compressed the 4-kilometer arms of the LIGO detectors by less than 1/10,000th the width of a proton. That is the most precise measurement ever made by any scientific instrument. Since that first detection, gravitational wave observatories have heard dozens of cosmic collisions, black holes merging with black holes, neutron stars spiraling into each other, perhaps even black holes swallowing neutron stars whole. What does this have to do with the Great Attractor? Gravitational waves open a new window on the universe. They let us detect massive objects that emit no light. They let us map the distribution of black holes and neutron stars across cosmic distances. They give us another tool for understanding the structures that shape our motion through space. Future gravitational wave detectors, including space-based observatories planned for the coming decades, will be even more sensitive. They might detect the subtle gravitational hum of supermassive black holes at the centers of distant galaxies. They might map the cosmic web in ways optical telescopes never could. The Great Attractor was discovered through careful measurement of light, but the next great attractors might be found by listening to the vibrations of spacetime itself. The Laniakea supercluster has not always existed. The Great Attractor has not always been pulling galaxies toward its center. There was a time when none of these structures existed at all. In the first few 100 million years after the universe began, there were no galaxies, no stars, no planets, just vast clouds of hydrogen and helium gas spread almost uniformly across the expanding cosmos. Almost uniformly, that word is crucial. The early universe had tiny variations in density. Some regions had slightly more matter than average. Some had slightly less. These variations were incredibly small, perhaps 1 part in 100,000, barely detectable even with our most sensitive instruments. But gravity amplifies small differences over time. The slightly denser regions had slightly stronger gravitational pull. They attracted matter from their surroundings, growing denser still. The slightly emptier regions lost matter to their neighbors, becoming even emptier. Over millions of years, the differences grew. Over billions of years, they became the structures we see today. The first stars formed in the densest regions, perhaps 200 million years after the beginning. These stars were giants, hundreds of times more massive than typical stars today, burning through their fuel in just a few million years before exploding as supernovae. The first galaxies coalesced from the gravitational collapse of enormous gas clouds. They were small and irregular at first, nothing like the elegant spirals and ellipticals we see in the modern universe. But they merged and grew, combining into larger and larger structures. Galaxy groups formed when nearby galaxies became gravitationally bound. Clusters formed when groups merged. Superclusters formed as clusters gathered along the filaments of the emerging cosmic web. The Great Attractor is the product of billions of years of gravitational evolution, a slow accumulation of matter, guided by the initial conditions set in the first moments after the Big Bang. We are falling toward a place that was destined to exist from the very beginning. The seeds of the Great Attractor were planted 14 billion years ago, and we are still watching them grow. The observable universe has a boundary. Not a physical wall or a barrier you could touch, but a limit set by the speed of light and the age of the cosmos. Light travels fast, but it does not travel instantaneously. When you look at a distant object, you are seeing it as it was when the light left it. Look at a star 100 light years away, and you see it as it was 100 years ago. Look at a galaxy 1 billion light years away, and you see it as it was 1 billion years ago. The universe is approximately 14 billion years old. This means the most distant light we can possibly see has been traveling for nearly 14 billion years. Anything beyond that distance is invisible to us. Not because it does not exist, but because its light has not had time to reach us. The edge of the observable universe is currently about 46 billion light-years away in every direction. Wait, how can that be if the universe is only 14 billion years old? Because the universe has been expanding the entire time. The objects that emitted the most distant light we see were much closer when they emitted it. Since then, the expansion of space has carried them much farther away. This creates a sphere around us, 93 billion light-years in diameter, containing everything we can observe. Beyond that sphere, there is almost certainly more universe, perhaps infinitely more, but we cannot see it, cannot study it, cannot even confirm it exists. The Great Attractor lies comfortably within our observable universe, only 200 million light-years away. We can study it, map it, understand its effects on our motion, but what lies beyond the edge? Are there other great attractors out there, other massive structures pulling on galaxies we will never see? Are there regions of the universe completely different from anything we know? We may never find out. The edge of the observable universe is a permanent horizon, and it is getting closer every day. 100,000 galaxies are being pulled toward the Great Attractor. Each of those galaxies contains hundreds of billions of stars. Many of those stars probably have planets. Some of those planets might support life. Are we alone in this cosmic flow? The numbers suggest otherwise. Even with conservative estimates, there should be billions of potentially habitable planets within the Laniakea supercluster. If life arises on even a tiny fraction of them, we could be sharing our journey toward the Great Attractor with countless other civilizations. But we have no proof. Despite decades of searching, we have found no confirmed evidence of extraterrestrial intelligence, no radio signals from distant worlds, no megastructures blocking the light of foreign stars, no visitors from beyond our solar system. This is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If the universe is so vast and so old, why have we not encountered anyone else?" There are many possible answers. Maybe life is rarer than we think. Maybe intelligent civilizations destroy themselves before they can spread across the stars. Maybe they exist but are deliberately hiding from us. Maybe the distances between stars are simply too great for any practical form of contact. Or maybe we are looking in the wrong places. The galaxies falling toward the Great Attractor span hundreds of millions of light-years. Any signal sent from the far side of Laniakea would take hundreds of millions of years to reach us. Civilizations could rise and fall in the time it takes a single message to cross our supercluster. We might not be alone, but we might be effectively alone, separated from our cosmic neighbors by distances so vast that communication is impossible. The Great Attractor connects us gravitationally to 100,000 galaxies, but it does not make those galaxies any closer. We are all falling together, but we may be falling in silence. The universe obeys rules, mathematical relationships that govern every interaction, every force, every motion through space and time. These rules are not suggestions, they are absolute. Gravity follows an inverse square law. Double the distance between two objects, and the gravitational force between them drops to 1/4. This is not approximate, it is exact. Every measurement ever made confirms it to extraordinary precision. The speed of light is constant, 186,000 miles per second in a vacuum, regardless of how fast the source is moving or how fast the observer is traveling. This strange fact, confirmed by countless experiments, is the foundation of Einstein's theory of relativity. Energy is conserved. It can change forms, moving from kinetic to potential to thermal, but the total amount never changes. This principle underlies everything from the motion of planets to the reactions inside stars. These cold equations govern our fall toward the Great Attractor. They determine our velocity, our trajectory, our ultimate fate. They do not care about us. They do not make exceptions. They simply are. Some people find this terrifying, the idea that the universe operates according to impersonal mathematical laws, with no room for miracles or special dispensations, can feel cold and empty. But there is another way to see it. The same equations that govern our motion toward the Great Attractor also allow us to predict that motion. They let us build telescopes and spacecraft. They let us understand the cosmos at a level no previous generation could imagine. The universe may be indifferent to our existence, but it is comprehensible. The same rules apply everywhere, from the smallest particle to the largest supercluster. And because the rules are consistent, we can learn them. The cold equations are not our enemy. They are the language of reality itself. and we are slowly learning to read it. The Laniakea supercluster is enormous, 520 million light-years across, containing 100,000 galaxies, with a mass equivalent to 10 quadrillion stellar masses. It is our cosmic home, the structure that defines our gravitational environment. But Laniakea is not alone. Beyond its boundaries lie other superclusters, other gravitational basins, other flows of galaxies moving toward their own centers of mass. The universe is filled with these structures, packed together like bubbles in foam, each one containing its own web of galaxies and clusters. The Perseus-Pisces supercluster lies in one direction, a massive concentration of galaxies roughly 250 million light-years away. The Coma supercluster lies in another, home to some of the most massive galaxy clusters in the nearby universe. The Hercules supercluster, the Shapley supercluster, the Horologium supercluster, each one a vast island of matter in the cosmic ocean. These superclusters are not randomly scattered. They are arranged along the filaments of the cosmic web, connected by bridges of galaxies and separated by enormous voids. The structure extends in every direction, as far as our telescopes can see, and we are moving relative to all of it. Our velocity toward the Great Attractor is just one component of our total motion through space. We are also being influenced by the Shapley supercluster, the dipole repeller, and countless other structures near and far. The cosmic flow is not simple. It is the sum of gravitational influences from across the observable universe. Mapping this flow is one of the great challenges of modern cosmology. It requires measuring the positions and velocities of millions of galaxies, then building models that explain how they all fit together. The Great Attractor was just the beginning. There are larger flows, bigger structures, deeper mysteries waiting to be understood. Laniakea is our home. But it is just one neighborhood in an infinite city. Here is a truth that some find disturbing and others find liberating. The universe does not care about us. The Great Attractor is not pulling us towards some cosmic destiny. It is simply gravity, operating according to mathematical laws, completely indifferent to whether anyone notices or not. The expansion of the universe is not punishing us by carrying other galaxies away. It is simply the nature of spacetime, unfolding according to the initial conditions set at the Big Bang. There is no plan, no purpose, no grand design that requires human beings to exist or to understand any of this. The cosmos operated for billions of years before our species evolved. It will continue operating for trillions of years after we are gone. Whether we live or die, thrive or go extinct, the galaxies will keep falling toward their attractors. The stars will keep burning their fuel. The universe will keep expanding. Some people find this depressing. If nothing matters on a cosmic scale, why bother with anything? Why study the universe if it does not care whether we study it or not? But consider the alternative perspective. If the universe does not assign meaning, then we are free to create our own. The fact that we exist at all, that matter organized itself into beings capable of asking questions about the cosmos, is remarkable. It may even be unique. We do not know of any other place in the universe where atoms have arranged themselves into astronomers. The Great Attractor does not care about us, but we care about the Great Attractor. We have spent decades trying to understand it, building instruments to detect it, developing theories to explain it. That curiosity, that drive to understand, is something the universe produced but does not share. Maybe meaning does not come from the cosmos. Maybe it comes from us, and maybe that is enough. We have traveled a long way together, from the discovery of our motion through space, to the mysterious Great Attractor, to the vast structure of the Laniakea supercluster, to the ultimate fate of the universe, in an era of accelerating expansion. Why does any of this matter? It matters because understanding changes us. Learning that we are moving at 390 miles per second changes how we think about our place in the cosmos. Learning that we are part of a supercluster containing 100,000 galaxies changes how we think about scale and significance. Learning that the expansion of the universe will eventually isolate us from everything beyond the local group changes how we think about time and permanence. These are not just facts to memorize. They are perspectives that reshape our understanding of existence. Every ancient civilization looked up at the night sky and wondered what they were seeing. They invented stories about gods and heroes, about creation and destruction, about the meaning of the lights above their heads. Those stories were not true in a scientific sense, but they served a purpose. They helped people make sense of a universe they did not understand. We have better stories now. Stories based on evidence and mathematics, tested against observation and refined over generations. Stories that are not just comforting narratives but actual descriptions of reality. The Great Attractor is one of those stories, a tale of gravity and structure, of cosmic flows and hidden masses, of a universe far larger and stranger than anyone imagined just a century ago. You started this journey sitting still, or so you thought. Now you know you are hurtling through the cosmos at incredible speed, carried by forces set in motion billions of years ago, falling toward a destination you will never reach. You are part of something vast, something ancient, something beautiful, and now you know it. Thank you for taking this journey. If you enjoyed it, please like and subscribe. There are many more mysteries waiting to be explored.